Hi, we're Team 9, and this is our final project presentation for ECE5553. So the purpose of the project was to apply the methods that we learned in the course to a realistic case study on autonomous vehicles. The project posed was an open-ended design problem with partial verification of the approach used, which required students to present their own designs orally and also in a written manner.
So for our choice of shuttle, we chose the 2018 Mercedes-Benz Sprinter passenger van. It was chosen because of its large seating capacity, as well as the fact that it's very customizable for what we would need it for. These are the parameters that we used. Most of these were found online, and they were used to help us in our simulations. So for the architecture of which sensors we needed, we initially went with a 360-64 Velodyne HDL64E for 360 LiDAR view. We put a triple-in PS300 long-range LiDAR on the front for long-range vehicle identification. We put a GPS on there for path following. We have two Delphi SRR2s for rear and side vehicle detection for lane changes. And then we also have a short-range LiDAR, the Hokuyo UXM LiDAR for turning. So this is a sensor diagram that shows where each of the sensors would be. It shows where the side range LiDAR as well as the long range LiDAR as well.
Now for low-level longitudinal control, we used the ACC generic model which was provided for us, and we removed the other vehicles and just used the single vehicle to simulate cruise control, adaptive cruise control. Okay, here's the formula which we based it on, which was given to us in class. Now the figures that we received from it were, here's the position tracking showing that the vehicle just increased position. This is our velocity control. This was the part that we really cared about. We wanted to make sure that we stuck below the speed limit and we maintained that. We have initial increase of up to 11.4, but we wanted to maintain under 9 meters per second. We had a big spike in acceleration, but that's to be expected, and that goes along with our adaptive cruise control model that we received.
The low-level lateral control, this is the linear model, which just takes the values from the equation, the low-level lateral equation. And then for the non-linear model, there is a PID controller which regulates the vehicle so that it follows the right velocity. This is the equation that the linear model uses. It inputs the data from there, and that's what the ideal situation would be like. And the nonlinear model, it exemplifies what a real-world car would show. And for the linear model, we first run it to get what we want to get, and the nonlinear model shows what we actually get, and we use the PID controller to readjust it so it gets closer values for slip angle and yaw rate. And we got a 0.025 radians difference for the slip angle, which is pretty close, and yaw rate, it was only 0.05. So both models were pretty good for our purposes, showing a real world example.
Okay, so now we are looking into path following and the collision avoidance stuff. So moving on, this is the state space model which is being fed into the plant, and these are the parameters which we just explained you in the previous slides. So this is the path following simulating model where we need to tune the PID first, then we'll set it into the non-linear plan, and after tuning it, we got the values as. So in the path following model, we got the PID gains, you can see here, which we got after linearizing the plan. We can see there is a controller, which is the PID control. Then we have vehicle path following model, state space control, and the trajectory calculation and distance calculation, which will be fed back again into the loop. And there you can see a first order transfer function which is acting as a filter so that the discontinuity in the path is removed. So this is the eastern town center map which we got after the locating the longitude and latitude points onto the Google Maps. We imported from there, and we need to localize these points. We got it in terms of x and y coordinates, And now we are focusing on the bigger loop over here, for which we set a Bezier curve into the loop, and which is divided into 19 subsections, so that we smoothen out the corners here, so that there is no problem in following the path. So this is the simulation results. You can see the vehicle is able to follow the path pretty closely, and we need to take care of one thing, that the vehicle is always going to the right direction, so the headway angle is to be taken care of, and it needs to be started at 0 and 0. So we set the point over there. You can see a blue dot in the plot, and this is the steering angle, and it's actually showing how the vehicle steered onto the path. This is the path error, which is actually the actual path and the difference between the reference path. So, and this is the road curvature. These two graphs are showing the vehicle heading angle and the yaw rate. So moving on to the collision avoidance stuff, we are focusing on to the avoidance of the obstacle which is being detected on the path, and as soon as the vehicle will detect it, it will stop. So moving on, this is the simulated model over here. You can see there is the obstacle box is there, which will come around at 70 seconds, and the vehicle is traveling around at 9 meters per second, which will detect it, and it will come to a stop after following the decision making straight flow diagram. So this is the decision making straight flow diagram, in which it's nothing but just if there is an object is being detected, then what the decision has to be made. If the error or the relative distance between them is less than 50, you have to brake, and it will go into the set mode 2, which is the emergency braking mode. And when the error is greater than 50, it just follows the lead vehicle. So these are the simulating results. You can see the ego vehicle velocity, which is our vehicle. It is actually following the lead vehicle. When it detects at the 70 seconds the static obstacle, it will come to a stop, and you can see it will remain under the vehicle position, which is around 1200 meters. Moving on, these are the results of the decision making, which shows what is the set modes, what is the error, and ego velocity set reference.
For the localization and the perception, so here is the example. The example shows how to perform the algorithmic detection and tracking the people in a video from a moving camera, and it is an ideal application for automatic safety. And these steps include the people detections, customize the suppression and the history to identify and illuminate the false alarm track. And here's some parameters. And besides the main function, there are also additional functions like the setup system objection function and the path skill table vectors. And here also there's some additional functions, the upgrade assign track function, and in the end there's a display tracking results function, which can display which can draw a colored bounding box for each track on the video, and the transparency of the box can be represented of the detection and tracks.
So this is a image of our state flow diagram. Basically, the vehicle is set to automatically follow a set path or the road. The other bubbles around it represent different challenges that it could encounter. If it encounters a vehicle, it goes into the vehicle following mode. If it encounters cross traffic, it would go into cross traffic mode. Here's our obstacle avoidance. Now we also do have a set of that where if it does hit the obstacle, it goes into the engine kill mode. So basically this just shows our vehicle how to go through its decision making.
So this is a list of real world challenges that we could run into. There's things like high pedestrian traffic, jaywalking, weather conditions, blocking signs and such, bad drivers, and high contrast between roads and from the sun and construction, and how risky they are. So high risk, medium risk, and then low risk. So high to low risk, and then for conclusion, we analyzed the Easton Town Center. So we got that the Sprinter passenger van was the best possible vehicle to use. We used it longitudinal and lateral control and the observed path to closely follow it. And basically we're pretty close to what we got. but a real world challenge to do, yeah.